Hello everyone, myself N.Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology, Hyderabad. So, in this module, we are going to discuss about thin plates which are subjected to bending and twisting. So, as you know that in the previous class, we have seen the thin plates subjected to bending and we derived the formula for bending of thin plates. Now, in this module, we are going to look for thin plates and we are going to extend the derivation from bending to twisting. So, the thin plates along with the bending, now if the shear loads are acting on it, then how the thin plate is going to behave. So, that is what we are going to discuss in this module. So, now, let's consider a thin plate which is shown here, and you can see here clearly that there are moments that are acting, which we call it as twisting moments, are acting on all the four edges. So, now here mxy is the twisting moment applied in a plane parallel to x-axis or in a plane. So, mxy is the twisting moment that is applied in x-plane, and on the edge opposite to it there is another mxy which is also acting parallel to it. And these two mxy are the twisting moments, they are applied parallel to x-axis. Now, similarly, there is myx on the other two edges. So, myx is over here. So, myx is acting parallel to y-axis, and on the other edge, another twisting moment, that is myx, is also acting parallel to it, parallel to y-axis. So, along with, already in the previous derivation, we have seen that we have used mx, applied bending moment mx on two edges, and we have applied bending moments my, bending moment per unit length my on the other two edges. So, along with mx, now what is the contribution of mxy for this plate? So, mxy basically it is a twisting moment, so it causes twisting of the plate. So, since it is acting on all the four edges, so the twisting of the plate will occur. Now, so mxy is the twisting moment intensity in a vertical x-plane and parallel to the y-axis, while myx is the twisting moment intensity in a vertical y-plane parallel to x-axis. So, now here we have mxy. So, it is very important here, mxy. Now, there are two suffixes here, as it is similar to the shear stress, that is the first suffix x, it indicates the plane on which it is acting. So, mxy means it is acting in x plane, and y means it gives the direction. So, the first suffix indicates its plane on which it is acting, and the second suffix denotes the direction of the twisting moment. So, mxy means the twisting moment acting in x plane in y direction. So, that is what we have to know about the first suffix and the second suffix of the twisting moment. And now the same, now what we are going to do here, like we take a section plane. Now, on this element we are going to take a section plane which is nothing but FD. So, taking section plane FD and redrawing the same diagram onto the right side, and then depicting the moments as they are there in the element. So, what are the moments we have here? So, we have mx, the bending moment over here, and my, the another bending moment per unit length, and along with that we have two moments that are mxy, which are acting in x plane and y plane. So, now here we are going to see, and as we discussed in the principal stresses, that there we have a normal stress acting on inclined plane and shear stress acting on inclined plane. So, usually we used to denote like sigma n is a normal stress acting on the plane, inclined plane, and tau theta is the shear stress acting on an inclined plane. Now, similar to that, the stresses sigma shear stress and the direct stresses acting on inclined plane, now we are taking the other two symbols, that is mt and mn. Now, mn is nothing but what? Normal moment acting on inclined plane. Similarly, mt is nothing but the twisting moment acting on the inclined plane. Now, we are going to develop expressions for these two. just as we have in the principal stresses. So we already know the derivations or the expressions for the normal stress acting on inclined plane sigma n and the shear stress acting on inclined plane tau t. So now we are going to, and also we have the formula, we have the stresses sigma x, sigma y, tau xy in the principal stresses. Now those sigma x, sigma y and tau xy are been replaced by mx, my and mxy. So we have the formula, that is, so how we are going to get this one? The normal moment acting on an inclined plane is given by mx cos 2 alpha and m plus my sin 2 alpha minus mxy sin 2 alpha. So from where we are getting this one? We are getting this from the principal stresses, that is normal stress on an inclined plane formula. Just here we are replacing sigma x, sigma y and tau xy and denoting by mx, my, mxy. Similarly, the twisting moment acting on an inclined plane is given by mx minus my by 2 into sin 2 alpha plus mxy cos 2 alpha. Okay, here also the sigma x, sigma y and tau xy are replaced by mx, my and mxy as just in the case of principal stresses. And also we have the angle of the plane on which it is acting, that is tan 2 alpha. So there you have the formula like tan 2 alpha is equals to minus 2 tau xy by sigma x minus sigma y. Okay, now this sigma x, tau xy is replaced by mxy and sigma x minus sigma y are replaced by mx and my, and rewriting the formula for tan 2 alpha. Okay, next, now coming to the diagram. So here we consider one two-dimensional element. Now we are considering one small elemental strip from that complete element, and we are going to denote all the moments that are acting on it and the corresponding stresses. Now you need to understand very clearly that how the moments are being depicted over here in this diagram. So let us consider one element, and let us consider delta x and delta y are their edge lengths, and also we are considering one neutral plane over here which is shown by n, and now we are considering an elemental strip which is at a distance of z from the neutral axis, and we are considering one small elemental strip like this here, this one and this one. Okay, and now what we are going to denote here? We are going to denote here the twisting moments first. So let us assume mxy is a twisting moment acting parallel to x-axis over here, and then mxy is acting on this edge which is again parallel to y-axis. And let us consider the thickness of this elemental strip as delta z, and now we know that the twisting moments mxy induces shear stresses in the plate. Shear stresses in the plate. So let us consider tau xy as the shear stresses which are equal and opposite on these two edges and depicting over here, and the thickness is considered as t, as we are considering neutral plane. Above the neutral plane it can be considered as t by 2, and below the neutral plane also it can be considered as t by 2. So this is very important to understand the diagram clearly, because we are going to write the equilibrium equation from the diagram itself. So always in aerospace structures, so first we need to give preference to practice the diagrams. So practice drawing the diagram and indicating all the moments and the distances and the lengths clearly over here, and because we are going to write the equations from the diagram only, so you have to give some practice for drawing the diagrams correctly with all the information in it. Now we are going to write the equilibrium equations. Now what is that equilibrium equation? And we have seen in the previous derivation also. What is that? The applied moment must be in equilibrium with the stress distribution. So now here the applied moment is mxy, and the stress is nothing but we are going to get shear stress. So the applied moment must be in equilibrium with the shear stress distribution which we have here. Now we are considering first phase A, B, C, D. So on the phase A, B, C, D, we are writing what is applied moment over here. Applied moment is mxy. Now we know that twisting moment, we consider twisting moment per unit length. Now this is acting on the length, which is, what is that length? delta y is the length. Edge is this one parallel to this one, and this edge length is delta y. So we have to write first mxy into delta y. That is the moment equilibrium onto the left side, and this must be equilibrium with the shear stress distribution. Now shear stress, we know that tau xy, and since that shear stress is acting over this area, it should be multiplied with this area to get converted into force. So now what is this area? This edge length is delta y and this edge length is delta z. So therefore it must be multiplied with delta y and delta z. Now this is for the element. Now if you want to integrate, and since we are writing the moment, now this becomes force. Tau xy into delta y into delta z becomes force, and the perpendicular distance is z, which we have to add over here. So now this is applies for only one small elemental strip. If you want for the complete plate, you have to integrate between minus t by 2 to plus t by 2, that is from the bottom of the plate to the top of the plate. Okay, so that is the equation we have here, mxy into delta y, that is equals to minus, one more minus sign is also there because the shear stress or the element what we are considering is below the neutral plane, in which we can consider the sign as negative sign. So similarly on face ADFE, now we are going to consider another face, that is ADFE on this face. So in the similar manner you can write the applied moment equilibrium with shear stress distribution, and therefore when you write, you will get mxy into delta x, that is equal to minus integral minus t by 2 to plus t by 2 tau xy into delta x into delta z is the area, and z is the perpendicular distance. Now if you look at these two equations, so delta y gets cancelled over here and delta x gets cancelled over here, and out of all these two equations you are going to get the same equation. So the similar equation you are going to get, and then you can write mxy equals to minus of integral minus t by 2 to plus t by 2 tau xy into z into dz. So this is the moment equation what we have here. Now here what we have, tau xy. Now we know that the modulus of rigidity capital G is nothing but the ratio of shear stress to shear strain, that is tau xy by gamma xy. Now what we are doing here, replacing the tau xy as G into gamma xy in the equation. So earlier we have tau xy, now this has been replaced by gamma xy into G, and rewriting this equation. So we have mxy, that is equals to minus G integral minus t by 2 to plus t by 2 gamma xy into z into dz. Now here gamma xy is nothing but the shear strain, and the expression for the shear strain is given by gamma xy equals to dou v by dou x plus dou u by dou y. So this is the formula for shear strain, which we already know that. Now this gamma xy, to express the gamma xy in terms of the deflection W of the plate, now what we are going to do is, an element is taken through the thickness of the plate, and that will suffer rotations which are equal to dou w by dou x, dou w by dou y in the xz and yz planes respectively. So that we will see in the diagram. So this is the diagram which we are speaking about. Now let us consider an element in the xyz plane, and then let us assume that it suffers rotation, and that rotation is given by dou w by dou x. Now that means what? A normal rectangular element, when you tilt it or when you apply twisting moment, it is going to twist by some amount, and now that amount we are calling it as rotation, and that we are taking it as dou w by dou x with respect to the any vertical axis. Okay, so now similarly here we are considering again edge plate length, edge length as delta x, and the neutral plane we are considering, and similarly we are considering from the neutral plane at a distance z, we are considering one more small strip, and let us assume the thickness of this small elemental strip as delta z, and now this has been dou w by dou x is the rotation, and the thickness also you can consider t by 2 from the neutral plane, and then now here the distance. Now this is the original position of the plate, and after it suffers a rotation of dou w by dou x, let us assume that its neutral plane position has been moved to this length. Earlier this was the neutral plane position, and we are considering that the displacement, that is nothing but given by minus u, because we are considering the left side of the equation or left side of the diagram. So minus u is the deflection, so minus u is the displacement. Okay, so now from this diagram we can write the displacement u in the direction of x at a point at a distance of z below the neutral plane, that is given from the diagram u equals to minus dou w by dou x into z. And similarly we can write the displacement v in the direction y direction, that is nothing but equal to v equals to minus dou w by dou y into z. Now once we get this u equals to minus dou w by dou x into z, v equals to minus dou w by dou y into z, we need to substitute in the formula for shear strain, which is equals to dou v by dou x plus dou u by dou y. Now it is the differentiation dou by dou x of minus dou w by dou y into z, which is v, plus, and now dou by dou y of what we have here, plus dou by dou y of u, which is nothing but minus dou w by dou x into z. Now when you differentiate this, so this is going to get minus dou square w by dou x dou y into z, and here also you are going to get minus dou square w by dou x dou y into z, and both of them you can add, and you are going to get gamma xy equals to minus 2z into dou square w by dou x dou y. Okay, now taking this gamma xy, the shear strain in terms of w, deflection of the plate, and substituting in the equation for mxy. Where is mxy here? Mxy equals to minus g gamma xy into z into dz. Now in place of gamma xy we are going to substitute, that is nothing but what we got here, that is minus 2z into dou square w by dou x dou y, and when you substitute you are going to get mxy, that is equal to capital G integral minus t by 2 to plus t by 2 2z square into dou square w by dou x dou y into dz, or it can also be written as, now here we have g. Now when you integrate this expression, now we have only z square. So z square integration, we know that it is z cube by 3, and when you substitute upper limit and lower limit, you are going to get the equation for mxy as gt cube by 6 into dou square w by dou x dou y. Okay, now also we know that g is the shear modulus, and which is nothing but there is a relationship between capital G and capital E. So there is a relationship between capital G and capital E, which is nothing but modulus of rigidity and Young's modulus, and that we are going to substitute here. And when you substitute that expression, that is G equals to E divided by 2 into 1 plus nu. Now when you substitute this in place of G, and the equation is going to modify for mxy, which is equal to mxy equals to et cube by 12 into 1 plus nu into dou square w by dou x dou y. Okay, and now so mxy we got this expression. Now after this, so mxy, that is equal to et cube by 12 into 1 plus nu into dou square w by dou x dou y. So this is the twisting moment contribution to the thin plate. So multiplying the numerator and denominator by the equation 1 minus nu yields the twisting moment deflection w of the plate. So however, we are getting this moment equation, twisting moment equation, right? So earlier we have seen the contribution of mx and my to the bending of the plate. Now this is the contribution of twisting moment mxy to the twisting of the plate. So when all mx, my and mxy act simultaneously, so we have to consider mx, my as well as mxy contributions for the bending and twisting of the plate. So that's it from today's class. So let's continue in the next module, that is plates subjected to distributed transverse load, in the next class. So thank you everyone.